Okay, so it's my pleasure then to introduce Ben Wormleighton from Washington University. He's going to talk about asymptotics of ECH via algebraic positivity.
Great, thanks for the invitation. It's great to speak here. It's great to see many of the people here who have inspired me as I've kind of dived into this and have helped along the way. This is going to be a bit of a field crossing talk where I'm by training an algebraic geometer, but as you see from the title, the kind of applications or the motivation here is very much symplectic in nature. Please feel free to, I'll try and explain any algebraic geometry that I use, but please do ask me to double click on anything if I don't explain it well enough. In general, I'm going to stick to a fairly sort of big picture discussion and be kind of selective on the details that I share, largely because actually almost some of the power of this technology is that it transforms very concrete questions into somewhat formal arguments on intersections, cohomology of divisors with real coefficients in algebraic geometry. So once the kind of big ideas are in place, the arguments themselves can be somewhat formal in nature. So I'll kind of share how to set up the situation, but I often won't follow through. But if you want me to dig into any of those details or anything else, Q&A afterwards is great, or feel free to stop me if you want a quick comment during the talk. So this talk is based primarily on these three papers. The first one, just me from earlier this year, the second with Julian Chides at Berkeley, and then a work in progress, which I might mention at the end, extending some of this to more general spaces. Okay. So the general context for what I want to talk about is a story which I'm sure is familiar to many of you, symplectic embeddings. So a central question is given two symplectic manifolds, x omega x prime, omega prime, let's say of the same dimension 2n, when is there a symplectic embedding between them? So namely, when is there a smooth embedding such that it plays nicely with the symplectic forms? The restriction of omega prime is omega. And when such an embedding exists, I'll use this kind of curly arrow with an S on top to denote that such an embedding exists, but I'm not specifying one. So the first kind of natural constraint is volume. You can't embed something of bigger volume into something of smaller volume. But from Gromov non-squeezing, this is really not a sharp constraint in general. So as a result, we're going to have to think about more nuanced obstructions if we're going to try and obstruct symplectic embeddings. So one of the first kind of main examples, which we'll bump into a few times in this talk, is the Gromov width, Cg of x omega, which is the supremum over the radii of balls, which symplectically embed into x. Okay, so I guess I should also comment at this point that symplectic embeddings kind of, there's two directions you can study these problems, kind of constructive and obstructive. You either want to construct particular embeddings or you want to obstruct the existence of embeddings. And when the two coincide, you have sharp obstructions when you have some data which is telling you exactly when or when not you can embed a certain space into another. And so the general focus, the general context of this talk will be on the obstructive side. So we'll be talking about obstructions to embeddings. Yeah. Okay. So the connections of algebraic geometry to these sorts of stories is not new. There have been many kind of milestones in the theory where the connections have been bridged. So let me just mention a few of them. So let's consider this construction of Macduff-Podorovich. So suppose we have an embedding, a symplectic embedding of a disjoint union of balls into the projective plane P2, so a ball packing. If you excise the interiors of these balls, then collapse their boundaries via the Hopf map, we're going to get n copies of P1. And this topologically is just the blow up in n points. Notice that I'm allowing the radii of the balls to vary. And these radii are encoded essentially by the following divisor, h minus some ri ei, The EI are just the exceptional divisors of the blowup, the P1s, and the H is just the pullback of the line class. And so from their work, it turns out that the existence of such an embedding is equivalent to there being a symplectic form in the class of this divisor on the endpoint blowup of P2. Okay, so it's in other words, this divisor or its Poincare dual is representable by a symplectic form. So one way of guaranteeing this is to ask that this divisor is ample. And this is a purely like algebra geometric notion. And so this is something that one can bring techniques of algebraic geometry to bear on. And actually, this particular example led to a very fruitful family of ideas exploited by Paul Baran and others, relating, the ampleness or positivity of this line bundle is very strongly connected to questions of Nagata's conjecture, big unsolved problems in birational geometry of surfaces. Like I said, this is one of many connections in this field of algebraic positivity, which I'm not really going to define, but that I claim that much of my talk resides in, is questions, especially quantitative questions about line bundles or vector bundles on manifolds or singular algebraic varieties. One of the key quantities that one considers in algebraic positivity is called the Syzygy constant. I'm not going to define it, but it's very much in play in questions like Nagata's conjecture. And there are lots of papers relating Gromov width of varieties to Syzygy constants on those varieties. There's been some recent work of Brendel, McAlkin, Schlenk, who construct some exotic embeddings of cubes. And this is done by this kind of beautiful construction using toric degenerations of Del Pezzo surfaces, a kind of very beautiful story that's woven into mirror symmetry, and many other stories across geometry. And so I'm just mentioning these stories to kind of give a sense of the history, give a sense that symplectic embedding problems have a kind of a very cozy, comfortable relationship with algebraic geometry, and that is in general the context that my talk kind of fits into. Okay. So the general structure. Now I've kind of set some common language. I'm going to start off by discussing more general obstructions to symplectic embeddings, focusing in on ECH capacities of Hutchings, discuss what their analogs in algebraic geometry like. I got muted there for a sec. Discuss analogs in algebraic geometry. So these are what I refer to as algebraic capacities, and then use this algebraic perspective, use the relationship between algebraic capacities and symplectic capacities to solve some problems of interest in symplectic geometry. Okay. Great. So the general term, I guess, for obstructions to embeddings are symplectic capacities. So I'll let script S be some class of symplectic spaces, let's say of dimension 2n, which includes the ball of radius, let's say all radii. I'm saying symplectic spaces here, really the most general thing I'm meaning is orbifolds. If you restrict to symplectic manifolds of some kind, that's also totally fine. We say that a function assigning to each space in S a real number is a capacity if, well, satisfies, for me at least, it satisfies these three properties. The first one's the most important. If there is a symplectic embedding from X into X prime, then we want C to be bigger on X prime than X. So in other words, C is kind of increasing with respect to embeddings, or in particular, it discerns or provides some obstructions to when embeddings exist. I'm also going to ask that C scales linearly with the symplectic form. Some authors would ask for something different. It's not too significant, I think, at least for me. And I want some non-triviality. I want the C of the unit ball is positive. It's an important collection of capacities which have found lots of uses so far in embedding problems are the ECH capacities defined by Hutchings. So for each symplectic 4 manifold, we're going to almost exclusively for the rest of the talk focus in dimension 4. These capacities give an increasing sequence 0, which is C0 of ECH, less than C1, C2, and so forth. So we have an infinite countable increasing sequence of obstructions to the existence of embeddings. So an example that I'll return to quite a few times, consider the ellipsoid with radii A and B to be the following set inside C2, or if you prefer R4, which, sorry, it's the ellipsoid. Notice that I scale by pi. I'll try and keep consistent with this, but I don't promise that I did. So in this context, the kth ECH capacity is the kth smallest number, which you can write as an integral linear combination. It's a positive integral linear combination of A and B. Okay, so the sort of thing this could look like, we start with 0, which is 0 times A plus 0 times B. Then perhaps A, in other words, 1 times A plus 0 times B, let's say, and then maybe we have A plus B, 2A, depending on how big A and B are relative to each other. So it's just this set of numbers written out in increasing order. And I'll denote the sequence by NK of AB. So two big results, which I'm sure much of the audience is convinced of why ECH capacities are things worth studying or considering. But two big results. The following was stated in different language, but the Hoffer conjecture, which became a theorem of Macduff in 2010, is that actually these ECH capacities sharply obstruct ellipsoid embeddings. I should have an interior here. We can embed the open ellipsoid EAB into ECD if and only if all these obstructions from ECH are met. Okay, so for all K, we have the CK ECH is bounded above, like so. Okay. The other kind of another kind of key property, nice property, which we get a lot of nice corollaries from, is this theorem of Christopher Gardner, Hutchings, Ramos, saying that asymptotically the ECH capacities just recover the volume constraint. So if you like, you can think of the ECH capacities as kind of increasing approximations of the volume constraint at infinity. So we'll kind of revisit this limit expression later on, but it's essentially saying that CK-ECH grows like a volume factor times square root K. Okay. Are there any questions so far? Great. Like I said, feel free to interrupt me or put something in the chat. Okay, so here's the example where I'm going to try and showcase the first place that algebraic geometry, at least in a we'll consider, comes into the story. So let delta AB be the triangle with vertices 0, 0, 1 over A, 0, 0, 1 over B. So observe that if you scale this triangle up by a factor of R, the lattice points, so the integral points inside this scaled up triangle, are exactly pairs of integers such that AM1 plus BM2 is bounded above by R. Okay, it's just a combinatorial problem. However, these AM1 plus BM2, they're exactly the NK ABs, or the ECH capacities of the ellipsoid. So this number of lattice points is exactly the number of K such that CK-ECH is bounded above by R. Okay, and when A and B are rational numbers, 1 over A, 1 over B are rational numbers. This is a rational triangle. And by Earhart's theorem on the growth of lattice point counts in dilates of polytopes, this is given by a quasi-polynomial, at least for integral R. So by a quasi-polynomial, I mean a polynomial with periodic coefficients. So I'm gonna show you a very similar slide. So when an algebraic geometer looks at that previous example, one might be tempted to translate it into something very similar. Suppose Y, P1AB, is a weighted projective space. So if you're not familiar with this, this is C3 without the origin modulo C star. So a lot like normal projective space, except the C star action is weighted. And so the quotient picks up some singularities. In the kind of toric, this is a toric variety in the sort of toric dictionary between polytopes and divisors, sections of a kind of distinguished bundle OYR on this projective space correspond to pairs of integers such that exactly the same conditions hold. And so once again, our count of capacities which are bounded above by a certain number is given by a quasi-polynomial, this time not by Earhart's theorem, but by the analog in toric geometry by Oberfold-Riemann-Roch, since the toric variety we have is an Oberfold. So this is sort of the main bridge or main suggestion. There's thing going on here. Moreover, if you take a generator of the class group, it's not quite the same as the Picard group, but it's, if you like, it's a kind of an effective, like an actual divisor that bases pic Q, pic tensor by Q. The complement of OY1 in P1AB is symplectomorphic to the open ellipsoid. So this is a generalization of the, I guess, the more well-known facts that P2 minus a hyperplane is symplectomorphic to a unit ball. Okay, so this is sort of the bridge that we're building between something in algebraic geometry and these embedding obstructions. Okay, so I'll pause here. I'm about to segue into the kind of the algebraic part of the talk. Okay, so the kind of motivation for algebraic capacities, these analogs to symplectic capacities, is the following setup. So suppose we have a four manifold X omega whose interior can be alternatively compactified up to an algebraic surface, to a projective surface, with the boundary divisor. In other words, the stuff that you've had to add in to make it compact, call that A. We'll then introduce some algebraic invariants on this pair, so the surface Y with this boundary divisor A, to recover the embedding obstructions, those ECH obstructions for X omega. So here's the definition, which I'll unpack. So suppose YA is a pair consisting of a normal projective surface. So here, just read normal as meaning an algebraic surface that I can do intersection theory on. With a Q-Cartier big R divisor A. I wouldn't worry so much about the word big if it's not one you've seen before. It's fine if you read ample here instead. And again, Q-Cartier is just saying that we're able to do intersections. If Y is smooth, we don't need to worry about this word at all. So given such a pair, and basically, as I've set it up, this construction I've made, these are exactly the sorts of objects that we would be getting from that situation I described on the previous slide, from those compactifications of open or interiors of symplectic manifolds. So given such a pair, define the kth algebraic capacity, CK alg YA, to be a certain infimum. So it's an infimum over a certain class of divisors of D dot A. So if you like, this is like the area of D using a form Poincare equal to A, such that the sum bound happening involving K for the Euler characteristic of D. And by this, I mean the Euler characteristic of the line bundle or sheaf associated to D. Okay. And then this chi OY is just some constant. And I guess the last thing I need to unpack before I kind of tell you really what this formula is saying is what is Nef. So Nef Y is a set of Nef divisor classes on Y. So this is the set of divisors D that pair non-negatively with every curve in Y. Okay. Okay, so let's take a step back. What are these invariants?
Can I ask just a can I ask a question about intuition?
Yeah.
So this is complex dimension 2. So being a divisor and being a curve is the same thing.
Yep.
But should I think of like A as being a curve or as a divisor? And similarly for D.
Great question. So yeah, okay. I'll say, okay, I'll revisit this right at the end of the talk. Basically, that choice of which one you're regarding as a divisor, which are you regarding as a curve, actually gives you, it'll give you two different things and two actually like potentially interesting things in higher dimensions. So I'm not going to pin down and say you should definitely think of it like this, but for this context, like for the kind of story I'm going to tell, you should think of D as being a curve and A as being a divisor.
Thank you.
Okay. Because we want to measure the area of D, basically. So the thing I was about to say is you should think of this as kind of, we're trying to minimize the A area of D subject to some kind of largeness constraint. And this largeness constraint, let's say this chi of D is actually just global sections, which in many cases, when we have good vanishing theorems, it will be. This is basically saying that the linear system containing D, in other words, the moduli of D, is sufficiently large. So this is really saying minimize area subject to sufficiently large moduli.
Great.
Yeah. Okay, and this simplifies very nicely when we have a situation where we have Noether's formula. This is kind of Riemann-Roch for surfaces. Where it simplifies even more, we see really, this constraint is a quadratic constraint, and CK-alg in this situation is minimizing area subject to this quadratic bigness constraint or kind of moduli constraint. Okay. Cool. Any further questions on that?
Well, what do you mean by, so why can it fail to hold? Because of singularities of
yeah.
Y?
Because I'm allowing Y to be, we don't have this formula in general. Like the classical Noether's theorem is proved only for smooth. I'm going to let Y have like overfold singularities, let's say.
If you replace, if all divisors are Q Cartier, it will work in general?
No.
Right.
Yeah, because I mean, for a start, this doesn't even have to be an integer.
Okay.
Yeah. So for example, my weighted projective space, I have that bundle O1. It's a perfectly good divisor. Its self-intersection is 1 over AB. Any further questions? Great. Okay. So let's look at a really concrete example. Let's look at Y, the projective plane, A, just OA, in other words, A times the line. Then the optimization problem here boils down to something extremely simple. CK-alg is just the infimum over positive D, or positive integral D of A times D subject to quadratic constraint. And to people familiar with ECH, this might look very familiar. It spits out this sequence of numbers: 0, A 2 times, 2A 3 times, 3A 4 times, and so on, which is exactly the sequence of numbers NK AA. In other words, the ECH capacities of the ball of radius A over pi. And this is indeed what we should have expected, because, well, let's say I pick A to be an integer. OA is describing the degree A Veronese A of P2. If you take out a hyperplane section, you get exactly this ball. Yeah, there should be no second A there. Okay. Okay, so let's kind of say one of the kind of main connective theorems this is a theorem of Julian Chaidez and myself from earlier this year. So suppose YA is a polarized rational surface, we'll just fix to rational, and that either it's smooth or it's toric. So in other words, we're allowing it to be singular, but only when it's toric. Suppose X omega is some star-shaped domain in R4. If there's a symplectic embedding from X omega into Y, then the ECH capacities of X are bounded above by the algebraic capacities of the pair YA. So in other words, these algebraic capacities do give embedding obstructions. And I should say, if it wasn't clear, that I'm regarding Y as a symplectic manifold just by picking some form which is dual to A, Poincare dual to A. Okay. So in particular, and the kind of one of the cases that we'll focus on the most, from many divisor complements, we obtain this bound, the ECH capacities of the complement, or say of a closure of the complement, are bounded above by the algebraic capacities of YA. Okay, and in many cases, well, I'll share a theorem later on saying a situation in which they're equal, but we expect this to be an equality in many, many cases. So this is one of the situations where I'm going to share the sort of the kind of main ideas in the proof, but not follow through. So there are sort of two components to the proof. First of all, we need to take the object, we need to relate the objects in the two infima. So the ECH capacities are defined by some optimization problem, some minimum in ECH. And the algebraic capacities are defined by some minimum. So I want to relate the objects which we're optimizing over in each context. The way to go from divisors to the sort of classes that are measured in the ECH capacities is via next stretching. So given a divisor D with kind of sufficiently big moduli, kind of denoted by these red points. So in this case, these red points are denoting kind of generic point constraints. And so my D should have like at least three-dimensional moduli. Given such a thing, I can produce an ECH class in degree 2k by next stretching, as depicted by this picture, which matches up with area, matches up with index. And so the point is that this procedure will give me, this will give me some relationship between the objects that I'm optimizing over on both sides. Then the ingredient I need to check that that actually those divisors I've got, that they actually count towards the infimum in ECH. The key here is Symplectic invariants, and that's where the Neff constraint comes in on the algebraic side, where we prove a great lemma saying that the set of Symplectic non-zero divisors well, actually contains the Neff cone. So Neff divisors are Symplectic non-zero, and that's how we tell that they actually contribute to this infimum. Okay, so that was just intended to be a sort of this is not the main theorem I want to talk about. This was just intended to be a kind of instructive discussion, just to give some sense of why those algebraic capacities should be measuring something that would obstruct symplectic embeddings. Okay, but I will pause for questions, which I may defer to the Q&A.
Can I just ask something about the previous slide, actually?
Oh, for sure.
So in that symplectic embedding, I'm a little bit confused about the role of A here.
Remember, it was defining the form on Y. It was doing the symplectic structure on Y.
I see. Okay, so I see. So like in the example of where Y is CP2, then A sort of controls the
exactly
size of that. Okay, I see.
Exactly. Cool. Any further questions? I'll jump back to the second slide. Great. Okay, so let me just say a few reasons why algebraic capacities have a chance at saying something interesting about ECH, why it's not just kind of a restatement. they're often more computable than ECH. So the real driving factor, maybe actually, I'll try not to skip between slides too much because this animation is pretty gross. But if you kind of jump back to especially this lower optimization problem, really the driver of complexity in this optimization problem is the NEF cone. D dot A is some linear function. D dot D minus ky is some quadratic function that we have like a reasonably good sense of. The real driver of complexity is the NEF cone, which in general can be absolutely insane. It can be a very sort of poorly understood object. For example, I mean, if you blow up P2 in 10 or more points, there are many conjectures about what the NEF cone looks like, but it's completely poorly understood. We understand only a small fraction of it. In the situations that I'll kind of move into, mostly the toric setting, it's the opposite. The NEF cone is polyhedral. This is some beautiful kind of convex optimization problem, which we have a shot at drawing some conclusions from. Okay, so when the NEF cone is reasonable, this optimization problem isn't too bad. So we have some chance of saying something. Even when the NEF cone is poorly understood, it's really easy to get bounds on ECH, or bounds on the algebraic capacities, and hence upper bounds on ECH, just by finding some divisor with sufficiently big moduli and looking at what D dot A is. And all this smart in inverted commas. This smart means we also can guess, at least for large K, that optimizers look a lot like multiples of A, and so that gives you a kind of a way of getting a not crazy estimate also. And so one of the main things that I'm going to try to discuss for the rest of the talk, algebraic capacities also kind of thrive in the non-generic setting. So in sort of the situation where, for example, this boundary divisor is not smooth, simple normal crossings, or I'll talk a little more about what I mean by non-generic once we get to the toric setting. But where symplectic techniques, at least to my knowledge, often don't do as well, there are actually the situations in which algebraic capacities thrive. So before I jump to the toric setting, are there any further questions or clarifications?
So maybe will you comment on when the two capacities are equal?
Yes.
From your oh, okay, great, thank you.
Cool. So yeah, for the rest of the talk, or most of the rest of the talk, I guess, I'll focus on toric manifolds, and a particular kind of toric manifold. So let mu be the moment map for the two torus action on C2. For some connected region omega inside the positive quadrant, define x omega to be the inverse image of omega under this moment map. So these spaces naturally come equipped with a torus action. These x omega are usually known as toric domains. So for example, and I guess you can take this picture to tell you what my scaling convention is on the form for C2. If omega is this triangle with horizontal length A, vertical length B, then x omega is exactly the ellipsoid EAB. So if omega has adjacent edges on the coordinate axes and is convex in some appropriate sense, then we say that x omega is a convex toric domain. In some situations, if you can get rid of the inverted commas, but for my context, I'm just going to be a little careful and assume it's convex plus some extra stuff. So if we have some property P of polytopes, we say that x omega also has that property. So for example, the triangle with vertices 0, 0, 2, 0, and 0, 3, the vertices of this triangle are all lattice points. And so we would say that this polygon is a lattice polygon. And hence we say that the corresponding convex toric domain, which in this case is E23, is a lattice convex toric domain. Similarly, if I consider the triangle with side lengths 1/2 and 3, this is a rational polygon. And so we say that E of 1/2, 3 is a rational convex toric domain. So it'll actually often be convenient in the following to work with this counting function, which has already come up in the example of ellipsoids I talked about earlier. But we'll define the cap function of, this is not x omega, this is YA, to be just the counting function. It's counting how many k are there such that ck alg is bounded above by x. Okay, so it's just the counting function for the algebraic capacities. Okay, and here's the theorem in response to the previous question. This is actually a theorem of mine from last year, which kicked off the work with Julian and many of the kind of other papers. So suppose x omega is a rational sloped convex toric domain. So rational sloped here just means that all the edges, you could possibly be rational, but all of your edges have rational slope. Okay. So if x omega is such a convex toric domain, we let y omega a omega be the corresponding polarized toric surface. So by this, we have some polytope omega with rational slopes. To this data, one can define a toric variety, like a closed toric surface y omega, and an ample divisor on y omega called a omega. So in this situation, we actually have that the ECH capacities of x omega are equal to the algebraic capacities of that pair, that toric pair. And in this situation, it's even a little bit nicer. There's a very nice vanishing theorem due to de Maizière, which says that Neff divisors on toric varieties. We don't have to worry about that higher cohomology. So actually, this is really the kind of pure statement that I said before. It gives that CK-ECH is exactly the infimum over the a omega area of D, subject to moduli is big enough, subject to global sections of D, or at least k+1. In the kind of dual optimization problem, if we assume that x is a positive integer, we also get that this counting function, cap x omega, is the max over the Neff cone of h0 D subject to this D dot A constraint. So it's just a restatement of the previous result. And I guess I haven't mentioned this so far. I'm being a little bit sloppy here. I can replace inf by min and sup by max everywhere that I've recorded them so far. So yes, this is a partial answer to one of the previous questions. Yeah, let me also remark that in this toric situation, there's a very nice combinatorial description of ECH due to Christopher Gardner, Choi, many other authors. And that work is one of the main ingredients in proving this theorem. It's why we get an equality here instead of an inequality like we did in the more general setting of rational surfaces. And this is, you can also view this as a sort of refinement. Indeed, algebraic capacities in general are a sort of, they're a method of converting ECH problems into convex optimization problems, at least when the Neff cone is like well behaved. And so you can sort of view that previous algebraic capacities theorem as being a generalization of the kind of combinatorial toric ECH. Okay, so actually before I jump into applications, let me pause again for questions. Great. Okay, so I'll talk about 3 applications, so 3 ways in which this sheds new light into symplectic embeddings. My main intention is to focus on the last one. So I'll talk about the first 2 in somewhat briefer terms before jumping into that last one. Okay. So similarly to convex toric domains, there's a notion of concave toric domains. And this is the case when our moment image has 2 edges, 2 adjacent edges on the coordinate axes, and in an appropriate sense is concave. So the sorts of things here, these are balls, ellipsoids. From work of Ramos, we can realize the Lagrangian bidisk as such a domain. And then a theorem, a consequence of the previous theorem is, which is due to Julian and I. Suppose YA is a possibly singular toric surface with an ample divisor A. And suppose that X delta is a concave toric domain, then the algebraic capacities completely obstruct or completely characterize symplectic embeddings of the interior of this concave toric domain into Y, where once again, Y is viewed as a symplectic manifold via A. Okay, so this is great. This is a situation in which we would control embeddings into a closed toric manifold, and we didn't need to appeal to any isotopy arguments. We didn't need to kind of construct an embedding into the interior and then move it off, and then or show that we could move embeddings off divisors at any point. This was like a purely numerical thing. Let me maybe say that kind of main ingredients in this, the previous results of mine and of Julian and I, tied with a really nice result of Dan Christopher Gardner, characterizing when concave toric domains can be embedded into convex ones, which is completely controlled, just as in the case of ellipsoids, by the ECH capacities. Okay. So as a sort of particular case of this, we obtained some special results on the Gromov width. So recall the Gromov width, once again, it's essentially the radius of the biggest ball that you can symplectically embed into X. And the theorem of Julian and I is that this is monotone under inclusion of moment polytopes. So I should point out here that this is maybe not so silly. These are the closed toric surfaces, potentially singular, associated to omega-1 and omega-2, in particular because of the kind of the way one constructs toric varieties from the moment image. There is not a map in any direction from y omega-1 to y omega-2, or the other way around. And so this is very non-constructive. But again, using the algebraic capacities as numerical obstructions, we pick up as sharp numerical obstructions, we pick up this monotonicity result. And this actually turned out to be a key ingredient in proving a conjecture of Virchow, Hofschier, and Nil. I'm not going to dwell too long on this definition. They have conjectured a combinatorial bound on the Gromov width of toric surfaces. It's given by something called the lattice width, some combinatorial expression. I don't really want to dwell on it. And we completed the proof of their conjecture as an immediate corollary of monotonicity. We obtained that if omega is some rational slope polygon, then the Gromov width of y omega is bounded above by this lattice width. So this is a purely combinatorial bound on the Gromov width. Okay. So in the remaining time, I want to just jump into talking about asymptotics. So you may recall we had a really nice description of the asymptotics of ECH capacities. That they grew essentially like volume times square root k, or a volume factor times square root k. The analog in this, there's kind of there's a factor of 2 floating around due to normalization, but we can reprove this for rational sloped convex toric domains purely algebraically. In fact, that's part of a more general theorem from my algebraic capacities paper. So suppose YA is again, it's a pair where Y is either smooth or toric. So if it's singular, it's allowed to be toric. And A is big and F. Again, you can just think of A being ample. That's totally fine. Then the limit as k goes to infinity of ck alg squared over k is 2a squared. Again, this a squared, you should think of it as the volume of this pair, and this is exactly capturing the same asymptotics as we're in the while law in ECH due to Christopher Gardner, Hutchings, Ramos. On a word on the proof of this. So the proof of this, this is one of those situations where there are a few ideas which reduce it to a kind of formal calculation on divisors. The kind of key device here is we have the Hodge index theorem in the case where y is smooth, and that tells us, at least for big K, what optimizers should look something like. And then we have to prove a kind of approximation theorem saying that the R divisors we pick up from Hodge index are close to Z divisors, which were the things we were using in the optimization problem for algebraic capacities. Cool. Okay, so what that previous theorem just said was that the algebraic capacities grow like this. They grow like square root 2a squared k. And so we can define error terms, just like there are error terms in ECH, EK alg, which is the difference. Okay, this goes, yeah. So we're just analyzing. We know that this is definitely O square root of k, little o square root of k, but we want to know exactly what does this look like. The analogous error terms in ECH, it's the same thing, CK ECH minus the thing we know it grows like. Okay, so when x omega is rational sloped, we get exactly that the ECH error terms are the same as the algebraic error terms, and so anything we deduce about the algebraic error terms will immediately apply in that context. Okay, there's been quite a bit of work, a few papers to try and control the growth of these error terms. There was a paper of Sun bounding this at big O. It was big O about k to the 0.4, and then Christopher Gardner Savale did prove big O k to the 0.4, and then in a recent paper of Hutchings, there's a bound for star-shaped domains in R4 of O to the k 0.25. But I think it's widely believed, at least for star-shaped domains in R4, probably more generally, that these error terms are actually bounded. So they're actually big O of 1. And indeed, this theorem confirms that the algebraic capacities are big O of 1. The algebraic error terms are big O of 1. So let Ya be a pair where Y is either, again, my usual assumption, it's either smooth or toric, with A big and nef. So there's this kind of funny condition. If A is a real multiple of a Z divisor, so in other words, if I can express A as A0 times a real number, then we can actually compute the asymptotics precisely. The lim-inf of EK is a half times the canonical times A, and the lim-sup is the lim-inf plus some constant associated to the pair. I wrote out what the constant is, but it's not something that, at least to me, it's not especially illuminating. Okay.
So
So,
may I ask a question? So you mentioned that the expectation is that the error is big O1. So what's the intuition behind that expectation?
that's a good question. I think a cheap answer to that, I suspect there might be better answers. A cheap answer to that is all known examples of big O1. Yeah, I personally don't have a great symplectic intuition for that. I would love to hear from somebody who does, maybe in the Q&A after. If that's okay.
Thank you.
Cool. So the main takeaway of this theorem is we have sharp in this kind of special situation where we're not quite rational or integral, but a real multiple of integral or a real multiple of rational. We have these kind of sharp bounds exactly on the asymptotic behavior of the EKs. And we can kind of visualize that what's happening is we're cycling, we're sort of periodically going, bouncing up and down from the limit to the lim sup. And that's what's happening. Okay. And so, like I said, because we have an equality between the EKs in algebraic and kind of algebraic capacities and ECH capacities for rational sloped convex toric, whenever this kind of weird integrality condition I had translates to whenever my polygon omega is a real multiple of a lattice polygon. So in particular, you know, if it's rational or or if it's integral, then the ECH error is 0.1, so it's bounded. And one thing I would observe is that this term, this kind of algebraic term that was appearing, this term involving canonical times A, at least in the toric setting, if you have anticanonical dot A, this is the lattice perimeter of the polytope A. So this is kind of it's measuring distance where one segment, one primitive line segment between lattice points has length 1. I think in Michael's papers he refers to this as the affine length. So this would be the affine perimeter. And so this captures this intuition that Dan Christopher Gardner often talks about, that subleading asymptotics should contain information about the boundary of omega, and this gets kind of refined in this context. So let me briefly say a word about where this comes from. So we deduce these bounds on the error term from the cap function. The cap function turns out to be a lot more convenient to work with. So when A is integral, show that for big enough x, this cap function actually satisfies a recursion. And so by recursion, what I mean is if D is optimal for that optimization problem I told you before defining cap, so the supremum over Neff divisors of global sections subject to area less than x. If D is optimal for cap x, then D plus A is optimal for cap x plus a squared. Okay, and so in this way, what happens is we generate a recurrence relation involving cap x and cap x plus a squared, which holds when x is big enough. That allows us to solve fairly explicitly for this cap function. It's given by some quasi-polynomial, but you can figure out what each of the terms are because you know that the period is given by this a squared. And then the subleading asymptotics, that's exactly sort of controlled by the subleading coefficients in this quasi-polynomial. So those kind of periodic coefficients which are appearing, the asymptotics are exactly controlled by those. And so doing a careful analysis of that function means that you can conclude those bounds on the error terms. But this was all under the assumption that A was integral. The nice thing is then the bound that you happen to get scales linearly, and EK scales linearly, and as a result, you get the same bounds for any real multiple of an integral divisor. So in the toric setting, for any real multiple of a lattice polytope. Okay, and I'll just observe that the place where I was using A as integral is that D plus A can't be optimal for this optimization problem if A is not a lattice polytope, or if A is not a Z divisor, because remember this optimization problem was over Z divisors. And so that's where I used that A was a Z divisor. Okay. Oh, I would comment that the one way you can get around this, you get an inequality in one direction, so only an upper bound when A is something more general. So for say if A is an R divisor, which is not a real multiple of any Z divisor, then you still get an upper bound by using a similar technique to this, but you don't get a lower bound. Okay. So my last few minutes, Actually, let me just pause for questions or comments about this just before I jump on.
Can you briefly recall why one wishes to understand this asymptotic so precisely?
Yeah. So one thing is you can actually get some new embedding obstructions from them. So in situations where you're trying to embed something, where you're trying to see if embeddings exist between things of the same volume, one of the things which obstructs embeddings is data associated to the perimeter, whether or not you can kind of fit the boundary inside, and that's something which you pick up by the error terms. So yeah, maybe I can draw this out in more detail in a second, but if, let's say, the volume of omega equals the volume of omega prime, then CK then CK of x omega is less than or equal to CK of x omega prime, if and only if EK of x omega less than or equal to EK of x omega prime. And then so in particular, the lim-inf of EK x omega better be less than the lim-inf of EK omega prime, x omega prime. And that says that corresponds to some bound on perimeter. So that's one reason. I don't think it's the motivate. It's certainly not my motivation. I think it's. I'm kind of. I've been convinced by Dan that these are interesting quantities that contain some information about omega, about x omega, and I want to understand that. And as with my algebraic geometry hat on, I want to understand what these subleading capacities and subleading asymptotics are saying about the algebraic geometry. Is that okay? Cool.
Thank you.
Okay. So in the last few minutes, let me just briefly say what next steps look like. So everything I described on the algebraic geometry side really fits naturally into this framework of algebraic positivity. In particular, some of the work of Macduff-Bolderovich relating to Chaudhry constants to Gromov width immediately gives us some relationships. If I get this inequality the right way around, we immediately see that the first algebraic capacity is an upper bound for the Chaudhry constant of the divisor A. And so, well, here's at least one relationship between algebraic capacities and other very classical objects of algebraic positivity. I would be shocked if there weren't more. One of the kind of current projects I'm engaged in is using toric in schemes. So these are sort of co-limits of varieties, if you like, sort of countable unions of varieties. And these, well, I know I recently proved that these objects are the kind of algebraic analogs to irrational convex toric domains. And so one can ask questions, pose questions about their asymptotics or about embeddings in terms of the geometry of toric in schemes, which is also interesting because the geometry of in schemes is under development. So there are many interesting questions there. My hope is that this will eventually lead to a proof that the EK are O1 in this context also. And then this is going back to the question Mohammed asked of viewing D or A as a curve or divisor. There are variations. You now have a choice about which perspective you should take in higher dimensions. And it turns out, really, as was kind of suggested by our proof mechanism, that thinking of D as a curve is good, that variations of the construction of CK-alg will produce embedding obstructions in higher dimensions. Julian and I are currently working on an algebraic avatar of the S1 equivariant capacities that Hutchings group have made use of. So that is all I wanted to say. Thank you for your attention. Thank you for your questions. Looking forward to talking more. Thanks.
Okay, thank you for that Very nice talk. So I guess we'll take a few questions now, and then we'll turn off the recording and we can have like an extended informal discussion if anyone wants to stick around. So are there any questions at the moment?
Yeah, so I had a very naive question about, these balls or these ellipsoids. I mean, they also have like, especially, you can think of them as having an analytic structure. Can you, but you're only talking about the symplectic topology. Is there some sense in which, because you have these algebraic capacities, there would be some kind of more subtle invariant if you actually had an embedding of an ellipsoid, closed ellipsoid with its actual analytic structure?
This is a good question that I don't think I have a good answer to. I think this is plausible from my understanding. Yeah, I don't think I have a meaningful comment. If you have more that you would like to say in kind of developing that question.
All I meant is, like, if it was embedded with its analytic structure, you could imagine trying to crush it and produce maybe some kind of algebraic space. And basically, I'm wondering, and of course, I'm not an expert in that. I'm just wondering if one can kind of show that understand how far optimal symplectic embeddings are from things which are analytic. And just one random thought is that to say, well, if they were analytic, then you could crush and produce an algebraic space, and maybe that would have some consequences, some further consequences that wouldn't arise just from being a symplectic embedding. Maybe that's all that's the extent to which I was wondering about the question. That's all.
I would like to say that, as far as I remember, Paul Biran in the 90s, when he was talking about these embedding questions, he was just embedding disjoint balls, but he did look at the difference between embedding them sort of in the complex analytic framework, keeping their analytic structure, and embedding them symplectically. And he had some mechanisms that would create some new embeddings that were complex analytic, I think. I mean, so there is a question about, we know that we can fully fill CP2 by 10 balls, say, or 11 balls, any number of balls. You can fully fill it by a square number of balls if you want to do it sort of algebraically, or keeping the analytic structure. But in general, it's unknown. And he was thinking about that question. So I don't know if there's anything in that old work of his that would be interesting, but that's certainly a question he looked at.
I guess maybe I'll ask, so you mentioned this this potential algebraic version of like the Hutchings capacities. So first of all, if you define something in higher dimensions, sort of the closest analog to the capacities you talked about in this talk, so that would be like some higher dimensional analog of ECH capacities? Like, is that just sort of nonsense, or what happens if you try to work with that definition?
Yeah, no, for sure. Right. So exactly. So this is exactly this answer to Mohammed's earlier question. This is exactly this like divergence between what do you think of as a divisor and what do you think of as a curve. So one option you could do is if you fix C a curve or a curved class, I can make let's say Y is some high dimensional variety. I can do exactly the same thing. Inf over the Neff cone of E dot C subject to, well, you know, the same thing I wrote down as before. Problem is, so let's say I specialize to the case where Y is a high-dimensional weighted projective space. In this case, the Neff cone is just one-dimensional. It's just that's an element H. If I pick sort of the minimal integral guy in here, the thing that I get is I get the exact analogs of the NK, you know, the thing that's listing out the integral linear combinations of A1 through AN.
Thank you.
And this is known to not be, I forget exactly what it is, but it's either not an embedding obstruction or a very bad one. I'm sure somebody here can confirm for me.
It's not,
so,
Not an embedding obstruction.
yeah, far away.
Yeah, there are embeddings that contradict that.
Great. So this one, the point being, this is bad. This is bad.
I guess maybe that is an embedding obstruction for just inclusions of polytopes or something like that. But I guess just
right.
But certainly not for like nonlinear symplectic embeddings.
Gus constructed embeddings that contradicted that. So there are known constructions of embeddings that contradict that.
So the point is that this one is bad. So the better thing to do, which is also, you know, from that kind of proof discussion that I did for from the result of mine of Julian's, it's much better to fix A, ample divisor, or big enough, and then define this as an infimum over curves. So traditionally, maybe you know this notation. This is the Mori cone. So this is effective curves of C dot A, subject to some constraint, and the constraint is sort of something which, at least in the Hutchings-Gut situation, it's not. It's different to moduli. It's actually a lot like your work with Juicer. This is some tangency condition, kind of order of tangency, in some sense, at some point to some divisor is at least okay. And then this object, at least for Toric, we've nearly proved, should recapture the S1 equivariant capacities in the Toric set, in the Toric, like convex Toric setting. So I guess the like moral to draw from this is that the kind of direct lifting of the algebraic capacities construction is not really symplectically interesting, at least from the perspective of embeddings. A variation of it, in which we're ranging over curves, is something interesting symplectically.
And is there any reason to think that the second thing somehow is about rational curves, whereas the top thing is about sort of all genus curves? Or?
Yeah. Oh yeah, for sure. Right. I should have been a lot more careful here. In the Toric setting, I think things are a little, might be a little more restricted. Right. I might really want rational curves here.
But anyway, it seems more sensible to me to make A a divisor, because then that gives you the symplectic form, right?
Right, exactly.
And you didn't explain the top one well enough to know where your symplectic form is.
Right.
So it's a bit mysterious to me what you're meaning there, and it's fascinating that you get this order of tangency. So I have you written this down yet, or are you doing that?
No, for the Toric case, again, like our guiding light for this, as was the case for that original theorem I proved in 2019, was the combinatorics. That was kind of like the guiding star of what should even the algebraic formulation look like.
Mm-hmm.
And then and then we kind of try and find a good geometric argument. And so the kind of combinatorial stuff is all there for this, or I think almost all there for this in the convex toric case when omega is rational slopes, etc. But yeah, a good like geometric argument we don't have yet, but we're looking into.
Mm-hmm.
But if you're interested, I can send you the like what we do have written up, or I can summarize it.
That would be wonderful. Yeah, I'd be very interested because actually Kyla and I are actually working on that paper again, trying to polish it up. Cool. So, we're very interested in anything related to it,
Yeah, absolutely.
So maybe let's thank Ben again, and then we can turn off the recording and then transition to the informal discussion.